All right, anybody remember that? All right, you can tell the leaving group quality from the pKa of its conjugate acid. That tells me how good or bad a leaving group is. If the conjugate acid has a really high pKa, it's a bad leaving group. If it has a low pKa, it's a good leaving group. Right. So what we're looking at when we look at the hydroxyl group, again, it's acting as a leaving group in a substitution, and the substitution step is either going to be SN1 or SN2, and that rate determining step is going to be determined by the loss of that leaving group. So when we do these alcohol conversions into alkyl halides, there's always going to be a step to turn OH into a better leaving group. That's one of the main aspects of these reactions. Right, so we treat it with a halogen source, and then we're going to get some intermediate we're going to get some intermediate in here where the OH group is going to be converted into a better leaving group. So we'll get an intermediate somewhere in here. But this is my alcohol now, and this is OZ, whatever Z is. Z can be whatever. We're going to talk about 3 different reactions, and that Z is going to be something different every single time. All right, so this is an intermediate. Put the H on there. Right, so that intermediate is going to be common to all of these reactions. You're going to get some type of reactive intermediate, whether hydroxyl group is now a better leaving group, and then that's when the substitution takes place. Shrink this down just a little. Shrink that part.
I have a question.
Go ahead.
Okay, so I know that a good leaving group has a low pKa. So you said the OH, the alcohol, is
not the leaving group itself, the conjugate acid of the leaving group.
Conjugate acid. Okay.
Mm-hmm. So if you want to know how good OH is as a leaving group, you would look up water, pKa of water, somewhere around 16 or 17, because water is the conjugate acid of OH.
Okay. Mm-hmm.
Right, so to measure the quality of the OH as a leaving group, you would look up the pKa of water. If it was some other group, some other functional group that you're trying to gauge how good of a leaving group it is, you look up the pKa of the conjugate acid. But in this case, it's going to be the hydroxyl group, because we're taking alcohols and turning them into alkyl halides. So the OH is always going to be the leaving group for this class of reaction. Right, but they all fall under the class of substitutions, and so here, black. So here you're going to have your product where X has now replaced the hydroxyl group, and then this will be plus. I'm just going to say H. Right, whatever this is, it's normally just a side product. We don't really care about it. Right, so again, anytime we're converting an alcohol to an alkyl halide, we're going to have to do two things. Number one, we're going to have to convert that OH group into a better leaving group because it's a really poor leaving group by itself. And then number two, we're going to have to determine whether or not the substitution step is SN1 or SN2, right? Because this is the substitution step right here. All right, questions about that before we start looking at some of these examples. So again, the leaving group, you can judge it by the pKa of its conjugate acid. All of these reactions that we're going to look at are substitutions. They all have multiple steps in the mechanism, but the rate determining step is the loss of that leaving group. So that's either going to be SN1 or SN2. And then the overall goal, again, is to take the OH and replace it with a halogen, right? All right, any questions about that? So we got, let me add in another page right quick because I need to make this point. About these different types of alcohols, right? So you have different types of alcohols, and each type of alcohol is going to call for a different technique, right? So if I have a primary alcohol like this, right, I need to use a certain type of reagent, right? There's some reagents that will work with primaries better than they work with others, right? If I have a secondary alcohol like this, I need to use a certain type of reagent, right? So the way I choose my reagents is by the type of alcohol I'm trying to convert, right? So some things will not work with primary alcohols. So I need to use something different. And that's all organic chemistry is finding the right tool to carry out a particular transformation. And then if I have a tertiary alcohol, right, these tertiaries have a specific set of reagents that they work with, right? Normally, if I have a primary, this is going to go through an SN2 type substitution, right? If I have a secondary, it can be either or, depending on what reagents you use. If I have a tertiary alcohol, it's going to be strictly SN1, right? If you recall from part one, SN1, give me one of the main characteristics of a SN1 reaction, or reaction that goes through SN1 mechanism. Anybody? Right? Any SN1 mechanism is going to go through an SN1 that goes through SN1 mechanism is going to go through a carbocation intermediate. That's the key difference between SN1 and SN2. All right. So this is going to be a tertiary alcohol getting converted into an alkyl halide. It's going to be stepwise. All right, SN2 is concerted. So no intermediate. And that matters when we write the rate law for that step. It matters when we think about the activation energy, the energy diagram, all of that, which we're going to do with each one of these reactions. All right, so let's look at, let's take this reaction. Let's start here. This is the easiest of the three. Mechanistically, all right, you can see here, I'm going from this OH, this alcohol, the secondary alcohol, to this alkyl halide. That's the goal of the reaction, again, to introduce a halogen. And in doing so, I'm going to substitute that OH group with a halogen. All right, so that's my product, alkyl halide, and this is my starting material, alcohol. All right, so with this reaction, the reagents that I use for secondary and tertiary alcohols, I use HX. Where X is a halogen. Right, normally X is iodine, bromine, or chlorine. Iodine is the most reactive out of all of them. When you think about using the alkyl halide as a precursor to something else, iodine is the most reactive because it's that bond is the longest and the weakest out of all of them. So when you make a alkyl iodide and you want to use it for another reaction, like say turning that alkyl halide into an organometallic, or using it in another substitution, or using it for some other type of reaction, then iodide is going to be your best halogen to use. So we're going to use that alkyl halide for another process. All right, iodine is going to be your best halogen. That bond is very easy to break. All right. We'll talk more about that when we talk about making organometallics. All right, so let's go back to here and let's just put some arrows in. All right, so I said that the first step is to usually turn the OH group into a better leaving group. So with this reagent, with the HX, in this case HI, what I'm going to do in this first step is a proton transfer. Right? What does that do to the OH? Right, you can kind of see it right here. Right, what am I doing to OH in doing that proton transfer?
I'm giving it another proton.
I gave it another proton. I also made it into water, which is a much better leaving group than OH by itself. So the way that this works, you remember this from part 1, right? The OH is going to attack the acid. This is acid-base chemistry. It's going to attack the hydrogen, and you're also going to break the HI bond like so. So you attack the hydrogen and you release the iodine as your eventual nucleophile, right? So it's acid-base, nucleophile, electrophile chemistry. All of this, none of this is, and the thing about these mechanisms, none of it is new. We learned all these arrow pushing processes in part one. And so this is not new, it's just a different application. All right. So now can somebody look up what the conjugate acid of water is? So the conjugate acid of water would be hydronium ion. Somebody look up the pKa for that.
It says negative 1.74.
Negative 1.74. All right, let's go. Let me jog you. pKa for water, which is the conjugate acid here for the OH. And I'm going to show you how effective, I'm trying to show you how effective this is as a gauge, right? So the water is the conjugate acid of OH, which this is the leaving group. And if we didn't do anything, that's what we would expect as our leaving group. So water has a pKa of 17. Look at the difference in pKa, right? That's what 17, almost 18 times. Hydronium is almost 18 times more acidic than water, or 10 to the 18 times more acidic. So it's a huge, there's a huge disparity between how good water is as a leaving group versus how good the hydroxyl group is as a leaving group. Do y'all remember that when we did that? Determining how much more acidic one acid is than the other in part one?
Yes.
10 to the delta pKa, the difference in the pKa. So here will be like 18.74 times more acidic the hydronium ion will be. All right, so now we've made water into made the OH into a better leaving group by converting it into water. And then let me put this over here too. All right, now we need to make that carbocation intermediate. How do we do that? This is the rate determining step right here.
Do you break the oxygen carbon bond?
Yeah, that's exactly what happened, right? You see that carbon is on this side is a carbocation now, and the only way to do that is take electrons away from that carbon. So we need to break this bond right here, like so, right? And we end up with a carbocation intermediate. All right, so that's my loss of leaving group, and in the next step, I'm gonna make my product. Right, so here's water that got lost. And then in the next step, that carbocation, which I have drawn here, is going to react with iodine. How do I show that?
You draw an arrow from.
That's my nucleophile. This is my electrophile, right? Arrows always flow how? Electrons. Always flow how?
Source to sink.
Source to sink. A nucleophile, excuse me. Nucleophile is my source. Electrophile is my sink. And so it always flows from source to sink. So that's how I get let me put the electrons back in over here. That's how I get that carbon iodine bond. And this whole section right here is the substitution part. Is it SN1 or is it SN2? What do you think? We just said up top, SN1 is stepwise, SN2 is concerted. If this was concerted, the iodine would just come in and directly replace the water. It would knock it out, right? It would come in and attack that carbon at the same time the water is leaving, but that's not what happens here. So is this SN1 or SN2?
SN1.
It's SN1. Good. Right. Anytime you see a carbocation intermediate involved in the substitution, that's indicative of it being SN1. Right. Anytime you see a carbocation intermediate involved in a substitution, it's going to be SN1. All right. So now let's think about another aspect of this. I'm gonna save this question right here because we'll do this later. I'm gonna copy it and actually put it on a new page because that's a great question. It's gonna help us to think through this even further. So I'm gonna put that down here. I'm gonna white it out up here so we can use this whole space. All right. So now if I ask you for that step, that substitution step, well, actually, let's do the whole reaction. If I ask you to draw the energy diagram, all right, what would that look like? What do we need to know in order to draw a reaction energy diagram?
The activation energy.
Well, we can't know that without doing the actual experiments. You're right in that we can estimate the activation energy for each step. But what do we need? We need to know how many steps there are in the reaction. Is that right? I mean, that's the main thing, because if we know how many steps, we know how many, for lack of a better expression, how many humps are going to be in that diagram. Is that right?
Yes.
So how many steps do we have here? We have proton transfer, we have loss of leaving group, and then we have the attack of the nucleophile on the carbocation. So that's how many steps total?
3.
3 steps. And then we said that the loss of the leaving group was the slow step. So what does that mean in terms of the activation energy of that step compared to the other 2 steps? Is it going to be higher or lower?
Higher.
Higher. Good. The slow, when we say rate determining step or slow step, that's the step that has the highest activation energy. And it could be exothermic or endothermic. In this case, we are breaking bonds, but we're not making any bonds to go to that carbocation. So it's probably gonna be an exothermic step. All right, but let's take that first step, that proton transfer, and let's just say, for the sake of argument, that step is exothermic and it's really fast. All right, so we're just gonna be here. All right, so this is star material. And this is intermediate 1, which is right here. Let me label it. Yeah. So that's my first intermediate. I'm gonna put that right here. Now that intermediate 1 is what gets converted to the carbocation. So that's my slow step. So how do I show that? Having more activation energy. What does that mean?
The chart should go higher.
I need to show, I show the activation energy here, don't I? All right, and we're saying that we're gonna go ahead and predict that it's endothermic. All right. We don't know how endothermic it is. We could calculate it, but that's not the point of this exercise. All right. So that intermediate is going to now go to the carbocation, which is intermediate 2. Let me put that down here. And then now that reacts with iodine. So that's my third step. And we're going to say that's exothermic and fast, right? So intermediate 2. It's going to react with iodine, and that's going to give me my product. All right. So this is a way to think about these reactions as well. We can think about the reaction energy diagram for a reaction like this. It has multiple steps, but this step right here is what we call, the rate determinant step. All right, because it has the highest activation energy. All right, any questions about the reaction, the mechanism, anything?
I had a question, but I forgot it. So if I remember it, I'll let you know.
All right. If it comes back to you, you can just ask it. We're gonna do one more. We got time to look at one more of these reactions. So actually let's look at this one. I can't understand. Oh, I know why. All right, let's look at this reaction right here. Notice the difference here is that this is a primary alcohol. And for a primary alcohol using HX, the reaction right, is going to slow way down. All right, so let's think about why. Does anybody have a hypothesis as to why, if we use HX with a primary alcohol, why would the reaction slow down? Think about what we just did up here.
Would it be because it's an SN2 reaction?
So you're saying this is going to be SN, is going to switch over to SN2?
Yeah.
Okay. Okay. That's a reasonable hypothesis. Why do you say that?
Because when it there's no carbocation intermediate, so I don't know, I was thinking the amount of energy would decrease. I don't know that's right, but
yeah. So you're in the ballpark. You're in the ballpark. When we think about this reaction, let's go through it again. So the first thing that happens is proton transfer. Is that right? Which is going to give us this intermediate. Oh, that's the right amount of carbons. I don't know. That's all right. We're going to roll with it. Was that right? That's my intermediate. Now this intermediate, and then plus, I'll just put plus chlorine. This intermediate, think about what happened up top. Right? If I, let me show it this way. right? If I were to simply lose the leaving group, I would end up with this carbocation, which is and then that would get, of course, react with chlorine like so. All right, what's wrong with that pathway? Why is that bad? I heard you what you were saying, Tia, and you are 100% correct. So tell me why the SN1 pathway for this start material is bad. What's wrong with that intermediate?
Um,
Think back to part 1. Think back to the trends that we learned for carbocations. What's the best carbocation that you can make? For a carbocation, right? Remember, it's tertiary is the best, secondary, primary, and then methyl.
is it because the can you go back?
Mm-hmm.
Like scroll. Is it because the carbocation is primary?
It's a primary carbocation. That's terrible. When you think about carbocation stability, primary carbocation is one of the worst ones you can make. Right? So this is a primary carbocation. That's bad. So that's going to make this pathway super slow, right? Because to get to that carbocation, it takes a lot of energy to get there because it's so unstable.
Mm-hmm.
So that unstable intermediate is going to slow this. Slow the reaction down, like way down to a crawl. All right, so you're going to slow that reaction way down. So what's the alternative?
To not have a carbocation.
To not have a carbocation, or in other words, to go through a SN2 type route where the chlorine comes in and attacks that carbon. Let me zoom in on that so I can make my arrows look halfway decent. So this comes here like that, and then you lose water, right? So that product for SN2, instead of going through a carbocation, is now going to go through a concerted mechanism. And then you end up with that plus H2O. And then let me put that water over here too. Right? So you end up having to go through with a primary, and this reagent, the HX reagent, you actually end up having to go through a different mechanism, right? But the reaction itself, that this is not conducive to converting primary alcohols into alkyl halides. You want to use a different method. And that's why we have other ways to do it, because using this particular method on a primary is bad, because that reaction is going to be super, super slow. That's why up here, I said that it works with tertiary and secondary alcohols. And this is the method you want to use if you have a tertiary or secondary. If you have a primary, you want to use a different method, which we're not going to start because I know we're not going to get a chance to finish it. But we'll look at what methods for primary and secondary alcohols up top. Because secondary, you can use this, or you can use either of the other two methods that we're going to discuss too. But primary alcohols, you have to use one of the other methods. This method, this doesn't work. It's too, it slows down to a crawl, and a reaction that should take an hour ends up taking, you know, several hours. Or you might have to run it overnight, and you still are not going to get a good yield. So you may as well switch methods. All right. So let me put that here. You want to use a different method if you have a primary. You don't want to use this method. That was the point of showing this example right here. All right, so we're going to stop here. Make sure that your name is in the chat so I can record the attendance, and we're going to pick up with this on Friday. Man, it's Wednesday already. And I'm going to post this again for those of you who may have come in after I posted it and didn't see the handout. All right. Any questions about anything before we depart?
Could you send an email